Let us try to understand about the example of timing analysis. So here we shall try to understand how the timing report will be present for arrival time and for required time, and how slack will be calculated. And let us try to understand about setup and hold as well. So these are the four scenarios which I have taken. So for first one, it is set input delay for max, and one more thing is set input delay min, and coming to set output delay max followed by set output delay min. So we already know max is used for setup, min is used for hold. Same concept is applicable here also. Max for setup and min for hold. So let us try to understand these four scenarios one by one in detail. So let us see about the example of timing analysis. Let us perform a sample timing analysis based on the concepts discussed so far. So till now we have understood about input requirement, output requirement, and we have seen about set input delay followed by set output delay. So coming to the notes, the timing report format will vary depending upon the tool used. The calculation method may also differ slightly, and understanding the basic calculation approach explained here will help you interpret any meaningful timing reports. So generally when you type as report timing, you will be getting a timing report followed by the timing parts that you are choosing. Like it can be either from input to register, register to register, register to output, or else from input to output. So here we will see a broader picture of how timing report and how timing calculations will be happening with respect to this particular example. So for this example, we will make explicit assumptions for various values as we proceed. The analysis will use the same circuit shown in figure 9.12. So based on this figure only, we have tried to understand about input delay followed by output delay. Now we shall give some of the random values for it. So random values are something like we will take some clock time period followed by some source latency, network latency, some setup time, and some hold time, followed by some of the delay values for C1, C2, and C3. And let us try to analyze how timing reports will be. So coming to the first scenario, input delay max. So this is something which is set input delay hyphen max. We already know like max input delay is used for setup analysis, and this condition should get satisfied. Like setup time means like required time should be greater than arrival time, then only we won't get any setup violation. And this is a particular figure that we are going to use for the analysis purpose. So this is block B1, this is block B2. So input delay is something which will be set from flip-flop F1, C1, C2. So the time taken by the data to reach this input port I1 is indicated with respect to the set input delay, followed by we will be taking some max delay value for this combo, and we will try to analyze the arrival time followed by required time, and we will try to analyze about the required time followed by the arrival time. Then based on the slack, we'll get to know whether timing is met or violated. So see this first one. So for this particular figure, I am assuming time period as 10 nanoseconds, and source latency is 0.5 nanoseconds, and network latency is 0.7 nanoseconds. So all these terminology we have covered in my previous videos. So please check those lectures before seeing this particular video. So see here at flop F3 in block B2. So we are trying to analyze at flop F3 which is present in block B2. So let us go step by step. First we will try to calculate about the arrival time. So arrival time is nothing but like it will have some clock to Q delay followed by C1 delay followed by C2 to reach to this particular point. So this complete thing is called as set input delay. Now when C3 gets added, then only we will get the total arrival time. So the time taken by the signal to travel from this point to data pin of F3 is something called as data arrival time. So this is some of the sample timing report that I have taken to make you understand this concept. So here time period is 10 nanoseconds. So in this I am assuming like signal is rising at 0 and it is falling at 5. Means we will get first positive edge trigger at 0 and second positive edge trigger at 10 nanoseconds. So based on that clock rising edge. So initially we are getting triggered at 0 nanosecond. So I'm taking the delay for this as 0. So active edge of reference clock assumed is 0, which is rising edge is active. So here this is positive edge trigger that is happening at 0 nanoseconds. So that's why here I'm taking a value of 0 nanosecond. Next, coming to the clock latency. So here two concepts will be there, that is source latency followed by network latency. Source latency is something like time taken by the signal to travel from clock source to the clock definition point is called as source latency, and from clock definition point to the clock pin of the flip-flop it is called as network latency. So I'm assuming some random values, that is 0.5 for source and 0.7 for network. So coming to the clock latency, it is taking 0.5 nanoseconds. So total 0.0 plus 0.5. So total previous it is 0 followed by 0.5 will give 0.5, and this is clock source latency assumed. Now I'm taking network latency as 0.7. So this 0.5 will get added up with 0.7 and I'm getting a total delay of 1.2 nanoseconds. So here notice clock network latency that we have assumed is 0.7 nanosecond. Next, coming to input delay. Here we are doing about max. So here this will be set input delay hyphen max, means it is taking some maximum amount of time to reach from this point to the input port of block B2. So it will have some clock to queue delay followed by C1 delay followed by C2 delay is something which is indicated with set input delay space hyphen max. So that value I am taking as 6. So 1.2 plus 6 will give 7.2 nanosecond. So here maximum input delay specified is 6. So the maximum time that we are assuming is from here to here it is taking 6 nanoseconds. So total time as we got now is 7.2 nanosecond till this particular input port. Now delay through C3. As we are going for max analysis, we have to assume maximum combo delay for C3. So this 7.2 followed by 1.2. Here 1.2 is the maximum delay that we are taking for this C3. So 7.2 plus 1.2 will give 8.4 nanosecond. So here maximum delay through C3 assumed is 1.2. So remember this point. Here I have mentioned it clearly. Max input delay specified is 6 nanosecond, means this is the maximum delay, that is clock to queue delay followed by C1 and C2. So clock to queue delay followed by C1 and C2 is nothing but the maximum delay, which is 6 nanosecond, followed by the combo delay of this C3 is 1.2 nanosecond. So this 8.4 nanosecond is the total time taken by the signal to travel from this clock to queue delay followed by C1 plus C2 plus C3. So the time taken by that particular signal to reach this data pin of flip-flop 3 is something which is called as data arrival time, and that value is 8.4 nanosecond. If you want it in terms of formula wise, this is the formula. Arrival time is something which will be source latency followed by network latency. So here this will have some source latency followed by network latency, that is for clock. Next it will have some clock to queue delay. So clock to queue delay is in flip-flop F1, C1, C2, C3. So C1 delay, C2 delay, C3 delay. So total if you add them, you will get the value as 8.4 nanosecond. So source latency is 0.5, network latency is 0.7, clock to queue delay followed by C1 and C2. You can see here clock to queue delay, C1 and C2 is something which is input delay, and that value is 6 nanosecond. I have mentioned it clearly here also. So that value I am substituting here, and followed with the maximum delay of combo C3. So maximum delay for the C3 is 1.2. So that 1.2. If I am adding all this, I am getting total arrival time as 8.4 nanosecond. Here I mentioned one formula. We know this already. Setup is something like required time should be greater than arrival time, then only there won't be any violation. So as of now I am getting arrival time as 8.4 nanosecond. So if required time is greater than this 8.4 nanosecond, then we won't get any setup violation. If not, we will get setup violation. Now here let us see about data required time. So as of now we have seen the arrival time, which is this path from here to data pin. Now required time is something like it will have some clock time period followed by some setup time of flip-flop F3. So here you need to remember, like setup time is something which is calculated from clock pin to data pin, that is called as setup, and there will be some more parameters like uncertainty and all. We have assumed some values. So let us see this particular report now. First coming to clock rising edge, as we are taking time period as 10 nanosecond, first we got first trigger at 0 and the second triggering is happening at 10 nanosecond. So total delay is 10 nanosecond for the second positive edge. So that's what I mentioned it here. Next positive clock edge trigger in the flip-flop. So here is something which we are calculating setup. So next edge is used for setup analysis. So it is 10 nanosecond. So first edge is at 0 nanosecond, second edge is at 10 nanosecond. So setup will be calculated at this second edge. Next, we are assuming some clock latency. Same values I am taking. Source latency is 0.5, network latency is 0.7. So initially that edge triggering is happening at 10 nanosecond. So it will have a delay of 10. Now this 10 plus 0.5, which is source latency, will give 10.5. Next network latency is 0.7. So this 10.5 plus 0.7 will give 11.2 nanosecond. Next, required time is something which is calculated at this F3. So this flip-flop F3 will have some amount of setup time. So generally setup time is something which is present between the clock pin and the data pin of that particular flop. So here we are taking that particular setup time as 0.3. So this is the value that should be subtracted from the total time that we got. So 11.2 minus 0.3 will give 10.9. So that's what I mentioned it here. Setup time is 0.3, which is subtracted from clock edge. So till now we got this value. Now there is some clock uncertainty. So clock uncertainty, I have made a video on clock uncertainty. So please check this video. So this clock uncertainty should be subtracted in case of setup analysis, whereas it should be added in terms of hold analysis. As we are going for the setup analysis, this 0.2 will get subtracted. Remember this point. It should be subtracted in setup analysis, whereas in case of hold analysis, it should be added. So that's why this 10.9 minus 0.2 will give 10.7. So this is the total required time. So data required time is 10.7. So we got required time as 10.7 and arrival time as 8.4. If you want it in terms of formula wise, it will be something like this. Required time is something which is total time period minus setup minus clock uncertainty, followed by we need to add source latency and network latency. So here time period I'm taking as 10 nanosecond. Setup time is 0.3, clock uncertainty is 0.2, source latency is 0.5, network latency is 0.7. So total if you calculate, you are getting required time as 10.7 and arrival time which we have seen from the previous slide as 8.4. So here this condition should get satisfied so that there won't be any setup violation. So required time is 10.7 which is greater than 8.4. So that's why there is no violation here. So slack is nothing but a required time minus arrival time, that is 10.7 minus 8.4 which is 2.3. Since the slack is positive, the setup timing on this path is met. If this condition is satisfied, here we will see something called as met. If not, we will see something called as violate. So coming to the overall summary, incremental time is something like delay introduced at the current stage. Total time is cumulative delay up to this stage, like previous total followed by the current incremental value, which is something like this previous value followed by additions or deletions which we are doing in order to get this particular value. Next, setup time is subtracted from the required time. So we already know about the setup time. Like setup time is something like before the active edge of the clock, data should be maintained to constant. Next, coming to clock uncertainty. So reduced slack can be added to data arrival or subtracted from the data required. So positive slack is something which is timing is met. Negative slack is nothing but which is violated. Means we get positive slack whenever required time is greater than arrival time, and negative slack is something like if this condition is not met, then you'll see something called as violation. Next, delay through C3, usually enumerated with all elements and nets in that path. So here as we are going for max, we are taking the maximum delay. Next, coming to clock latency values, used when clock network delays are not propagated. Otherwise, the clock path is fully enumerated with all the elements delay. So this is some kind of a summary which I have mentioned it here. So in this video, we have understood about set input delay followed by hyphen max. In the upcoming videos, we will try to understand about set input delay hyphen min, followed by same concept is applicable for set output delay as well.